Fires are part of the natural ecosystem, and indigenous people manage them. So we're living in an era of climate change and experiencing megafires. What we've been seeing over the last couple of decades is an increase in the intensity of fires. So fires are burning hotter, longer, and getting bigger. And this is not going to go away. What the lab is very interested in and committed to is understanding how to reduce the risks posed by these fires that we're living through, and also mitigate them by managing forests and also understanding more what the health impacts of the smoke are. So what happens in megafires is they're burning so intensely that they emit smoke, and the heat lofts the smoke high. And the smoke also, if there's moisture in the upper atmosphere, can be lofted further high by cloud formation, like pyrocumulus. And once it's high up there, just like an aircraft, in the jet stream, these smoke particles or plumes can go long distances, just like weather fronts. And then when they descend over New York City or Washington, D.C., the smoke gets to the surface and exposes people. This is a documented fact. What Los Alamos has done is it has developed the first physics-based fire model, particularly in complex terrain, to understand how fire spreads and help firefighters. We have then expanded the physics of the fire spread to the vertical rise of the plume and interactions with environmental conditions to predict pyrocumulus and storms.
I'm speaking on the weather side of this. We get a significant portion of our rain here from a monsoon. And when you get so much smoke now, the smoke can first inhibit solar radiation coming down and heating the atmosphere and then causing clouds to form. And two, because there's so much smoke, it produces only small cloud droplets that can't produce rain. So it's a compounding effect. And if this continues, it's going to have a big impact on our monsoon and the amount of rain that we get here in this area. But Los Alamos now, I've been modeling wildfires for 28 years. And I started with the South Canyon, me and Rod Lynn started with the South Canyon fire, which was 2,000 acres. Unfortunately, it killed 14 firefighters. And that's what motivated us to develop the models that we use to study wildfires. But as that was 2,000 acres. Over the years, we've seen the fires go from 2,000 acres to 50,000 acres to 100, now to 400,000 acres. As they've transitioned from small to large, the change on the atmosphere has been equally as large. And that's something that we're really trying to understand. What's going on from these small fires now to these large fires? So we've developed this sort of multi-scale approach to go from modeling the details of the combustion, then modeling, let's say, the larger impacts of these large megafires now, and next, the impact on climate, the global impact.
Wildfire smoke impacts people in different ways. We have experience on the ground where we get smoke delivered to us, and we know we don't want to breathe it in because we know that it causes us to cough and maybe just generally not feel good. There are a lot of components of smoke that can negatively affect our respiratory systems. We don't necessarily know what all of the chemistry is that affects those impacts. And that's one area that we're trying to actively research. But we know just particles in general, when we breathe them in, have negative health impacts. We know that smoke is a complex mixture of a variety of different chemical compounds. But models can't handle all of that different chemistry. It is too computationally expensive. So working with our observations that we make in the lab and the chemistry that we know is happening, we develop some reduced order parameterizations that can be put into models. And based on some of our initial work, it looks like these parameterizations do a good job of reproducing observations in the data. And this is much better than not including any chemistry at all, which sometimes has been done in the past.
Wildland fire affects approximately 70% of the terrestrial ecosystems in the world. And of that, around 50% is what's considered a fire-dependent ecosystem. And so by that definition, fire defines the ecosystem, and without fire, you no longer have that ecosystem. So here at Los Alamos National Lab, we're now linking ecosystem demography models and hydrologic models to those fire behavior models. Here in Los Alamos, we've been affected by wildland fire, and one of those fires in 2001 was an escaped prescribed fire. And this really nails down why we want to get the science behind prescribed fire down. Because on one hand, we know we need prescribed fire to reduce fuel loads and wildland fire risk. On the other hand, prescribed fire is an inherent risk and it can get out, endanger our own property and lives with an escaped wildfire. So it's a very tenuous balance that we're trying to strike, but it's something that we know we need to do. What you're seeing here is a very patchy landscape, which happens a lot in these larger wildfires. But one of the things that's surprising is, in contrast to the aspen that are coming back here and up there, these south-facing slopes, especially that far ridge, you're seeing that high severity fire where the vegetation is just not coming back. And if we were to contrast this with, say, a lower severity fire or a prescribed fire, we might have been able to preserve some of those other forested stands.
Coupled fire atmosphere models, like the ones that we're developing, can be used for a variety of things as we go forward in the future. They can be used to look at event reconstructions or training or lessons learned from wildfires. They can be used to better understand the fundamental phenomenology of fires and smoke lift. They can also be used to do better planning for prescribed fires or understand what fuel mitigation effects might be on future wildfires.